meeting. And it's good to see everyone. And I'm very excited today to introduce our guest speaker. I've been volunteering with him since August at the Museum of Natural Sciences. And Sean Moran is currently doing kind of double duty because he's having to do geology and paleontology, but we're hopeful that that will change soon so he can just be paleontology. But he's going to give us a great talk today on Badlands mammals in the time of Oligocene cooling. So I'm really excited to hear that. And so I'd like to turn it over to Sean and let him tell us a little bit more about himself and then get started on his wonderful talk.
Great. Thanks so much, Terry. Go ahead and try to share the screen. I will say it's been a while since I've been on Zoom for long periods of time. So for a talk this long, we'll see how it goes. I'm happy to answer questions as we're going through the talk. I think there's the function where you can raise your hand to ask any questions as we're going through. So feel free to make use of that. I'm happy to stop at any point and discuss things further. I'm hoping for this to be around 40, 45 minutes, and then we'll have a little bit of time for questions at the end. I wanted to thank you all for having me today. It's really great to meet you all. I started this past May, so I've been here for about a year now. And it's a weird time to get started at the museum with the pandemic and everything. So I've had the good fortune to meet some of you, but few of you, and I hope to continue working with you in the future as I become more ingrained in the museum here. So just a little background on myself to get started. Let's see if we can get this going. There we go. So just a little background on myself. So I am one of those people who is just always interested in studying ancient life and fossils. I can point to 5th grade as the period in time when I became very interested in the study of past life. I had a teacher who lived next door to a professor at the University of Pennsylvania who was an archaeologist working in India, and she came into our classroom and gave us a talk on some of her field work, and it got me really jazzed about the idea of someday doing my own field work and researching past life. At that point, it was archaeology. I was always interested in fossils and dinosaurs. And it became pretty clear early on that as a 5th grader, it's really difficult to do archaeology or anthropology. But I grew up in South Jersey, and across the state, as in North Carolina, there are many creeks that are filled with Cretaceous fossils. So starting in middle school, I convinced my dad to take me collecting shark's teeth up in Monmouth County, Big Brook and Reminiscent Creek, which some of you may have heard of, may have been to. Later in middle school, I was lucky enough to start volunteering at the Academy of Natural Sciences in Philadelphia, where I was primarily working on dinosaur fossils, preparing, talking to the public and guests about the preparation work we were doing, but also out in the fossil hall, describing the history of paleontology through the Academy of Natural Sciences. In high school, one of the lab leaders came to me, invited me out to Montana for a few weeks to do some field work in the Hell Creek. And this was my first real field experience. And I absolutely fell in love with being in the American West, looking for fossils and trying to understand past life. And I kept going out. This was, I think, between my sophomore and junior year of high school, and I kept going out to the same ranch pretty much every summer through high school and into college. At the end of high school, I thought this was a career path that I really wanted to pursue. So I looked at a bunch of different schools, and I ended up at the College of William and Mary in Williamsburg, Virginia. And at this point, I was really sure I wanted to do vertebrate paleontology. That's what I was most interested in. And the paleontologist at William and Mary was an invertebrate paleontologist. But she had some really amazing connections and was able to teach paleo in a way that really connected with me. And through that process, I really became to love geology as well as paleo, and sort of broadened my interest in the field. One of her lab mates, when she was in grad school, worked at the Smithsonian. So between my sophomore and junior year, she connected me with him because he was a vertebrate paleontologist. And he connected me to some field work he was doing out in Wyoming. And one of the reasons I fell in love with this so much was when I was out in Montana in high school and early in college, one of my favorite parts of the Hell Creek to collect were these little microsites in the top right corner. And these little microsites were chock full of things like this Champsosaur vertebra. There's a little lizard jaw here. There's a few fish scales in here. And it really gave an idea of what the entire ecosystem looked like than just digging up one dinosaur. So this was an area of research I was really excited in. And through the summer of interning with Dr. Corano, it gave me the opportunity to really collect these sites, but also to understand what was happening on the level of the ecosystem and the geological processes that were forming these sites. So I continued that to my senior research project, where I went back out to the Hell Creek and collected about 5 or 6 of these microsites and tried to tease apart some of the fine details in how these sites were actually being formed. What were the processes forming these sites, and how did that affect the animals that we were seeing in each of these different types of sites, whether they were being formed by rivers or lakes, or the reworking of these lake deposits. While I was at the College of William & Mary, it also gave me the opportunity to do a lot of other fossil collecting throughout the state of Virginia up into Maryland, and I continued some of my research and collection up in New Jersey as well. So in 2011, I finished at William & Mary and was trying to figure out what I wanted to do from there. And I ended up applying to grad schools and ended up at the University of Florida. So I started my master's at UF at the Florida Museum of Natural History in 2011. And one of the things that really drew me to this program was that they were just starting a project in the Panama Canal. So as we know today, the equator and around the equator is a hotspot of biodiversity. Unfortunately, in the fossil record, it's really difficult to see that because we have so much vegetation around the equator. So there aren't too many outcrops where we can really study the fossil record in the past to look at these biodiversity hotspots. In the mid-2000s, we were lucky enough that the Panama Canal was being expanded and was cutting through rocks that were about 23 to 20 million years ago that preserved some of this fossil record. So this is a really exciting opportunity to go to Panama and really discover what was happening 23 to 20 million years ago in the rock record. But also being at Florida gave us lots of other opportunities. We went to the Bahamas to look at some Pleistocene cave deposits. Florida itself, as you all know, is a hotbed of paleontology. It's hard to go anywhere without finding a fossil. So there were plenty of phosphate mines we went to for field trips. And there are a lot of local fossil sites too. So starting in 2015, a local farmer found a fossil site that's late Miocene, about 5 million years ago, where we're finding thousands and thousands of fossils every day. Since 2015, I think there's something like 120,000 fossils from that Montbrook fossil site. So because Florida is underlain by all of this limestone, all this karstic material, we get lots of these sinkhole features, as well as some river deposits, which really makes for an exciting place to do paleontology. One of these other sinkhole deposits that was found in 1930 is the Thomas Farm site. And this is one of the most important sites of the early Miocene, really anywhere in the world. And this gives us a glimpse into what the ecology was like about 18 million years ago. So over this near century of research and collection at the Thomas Farm site, we have somewhere in the ballpark of 500,000 fossils spread across several collections, notably at the Florida Museum and at Harvard. So because we have such a large sample size of fossils from the site, we can really look at some of the fine details about how evolution is happening on a very fine scale. So this picture on the left is this Thomas Farm site, and these on the right is an associated dentition of these 3-toed horse fossils from the animal Parahippus leonensis. So what's really interesting about Parahippus is it lies at the base of the radiation of all modern grazing horses, but it itself was still mostly a browser. So as we know today, horse teeth are really long to combat high wear rates with grazing, but you can see from these horse teeth that they were still relatively short because they're eating mostly leafy vegetation. So my master's project was taking geochemical samples from these horse teeth and looking at the stable isotopic signature to figure out what the climate was like when this horse was living at Thomas Farm, as well as to try to tease apart some of the nuances of what its diet looked like when it was living. So after I finished my master's in 2014, I was sort of in this position where I wasn't sure what I wanted to do next. And one of the things I became involved with at the museum was working a lot with fossil clubs and teachers through the My Fossil project and several education projects we were working on where we were taking teachers out to the field or creating paleo curricula for classrooms. And this led to several fossil trips to northwestern Nebraska and the White River Group. In 2016, after working for the museum after my master's for a couple of years on these projects and some collections projects, I realized this was an area I was really interested in doing research in, and this became the focus of my dissertation, which I'll get to in a minute. So now to today. So in May of last year, I started my new position here at the North Carolina Museum of Natural Sciences. So I'm in charge of the paleo collections, as well as the geology collections. And what I am really excited about this position for is that we're in a position where we're in a state in North Carolina where we have a really great fossil record. And our museum does a really good job of documenting a lot of that. But coming from my background as a Cenozoic mammal paleontologist, there are certainly gaps, particularly in the Oligocene, such as from the Belgrade Quarry, and the Pleistocene, where we can really fill in some of this knowledge about North Carolina paleontology. So I'm excited to be here today to talk to all of you, to get to know you, hopefully to join you on field trips at some point in the future, and to start building out some of our knowledge and research and collections in some of these gaps we have in collection. All right, so now back to Nebraska. So just out of curiosity, how many of you have been to Nebraska to look for mammal fossils? I see Joy's hand. So a few of you. So you're likely to know a lot of the background about paleontology in this area of Nebraska. What I'm going to go through is why I think it's a really exciting time to study. For those of you that have been out there, you know how fossiliferous it is. It's hard to walk across the Badlands in Nebraska or South Dakota and not step on 10, 20 fossils in the span of an hour. And this gives us a really large sample size to look at and to understand these really fine scale changes in some of the animals we're seeing, and how we can relate that, given the period of time that is recorded here, to what's going on a global scale and global climate change. So just a little bit of background. So if we take a look at this graph on the left, so essentially we're just looking at climate over the past 65 million years since the extinction of dinosaurs. Everything on the right of this graph is relatively warm periods of time. Everything on the left gets cooler. And there are just a few things that I want to point out on this graph. So one of the major events that we can see is this large positive increase in these oxygen isotope values right at 55 million years ago. So this is a period of time called the Paleocene-Eocene thermal maximum. It's a very rapid global warming event that's been heavily studied in places like Wyoming and has been a real source of inspiration for my own research. And I'll get into that a little bit more later. And what we see is a very rapid increase, about 6 to 7 degrees Celsius over a couple 100,000 years. So a pretty good analog to modern day climate change. And we have a really great fossil record in the Bighorn Basin of Wyoming, where we can see how animals are responding to this rapid shift in climate. If we look closer to today, we see these glacial and interglacial times, high variability in global temperatures. When we have mostly ice-free times in the interglacials, and then these major ice ages. So much more variability here. But one of the other major events we see on this graph is right at about 34 million years. And this is the Eocene-Oligocene transition documented in the rock record of the White River Group. And why this period of time is so exciting is because it really separates the greenhouse world of the first 30 million years or so of the Cenozoic, of the age of mammals, from the icehouse world of the more recent 34 million years. And on the right side of this graph, this is showing polar ice. So at this time, 34 million years ago, we see permanent polar ice forming on the South Pole. And then closer today, we start to see permanent ice on the North Pole. So this is a really interesting time to see what is happening to fossil taxa due to this climate event. And if we look at extinction curves across the Phanerozoic, we see many of the 5 major mass extinctions. So here, KPG boundary, extinction of the dinosaurs. Over the past 66 million years or so, we don't see too much relative to prior to the KPG, but we do see this major peak that happens to occur right at the Eocene-Oligocene. This is driven mostly by marine invertebrates, but this is also known as a period of time called the Grand Coupure in Eurasia, or the Great Cut, where we see large taxonomic turnover of mammal faunas in Eurasia and more recently in Africa. Interestingly, despite the fact that we have almost 160 years of history of collecting the White River Group in North America, the general narrative to this period of time is that North American mammal faunas don't really respond to this event like we see in the rest of the world. And that's sort of what is driving my research. Is that actually a biological signal, or is that due to the way we have collected the Eocene-Oligocene transition in North America to this point? So kind of diving into the White River Group. So this is a series of rocks best known by Badlands National Park in southern South Dakota. So if you've ever been to the Badlands, you sort of know what these rocks look like. They're kind of drab colored rocks. They're not the beautiful variegated paleosols that you might see at Petrified Forest, Terry, that you might see in Wyoming. There are places where we get this really great paleosol formation, but where I'm working in Nebraska, there's not much of that. In the Bighorn Basin and the PETM, we have these really great variegated layers where you can almost say, if you're in this red layer, you know you're in this very narrow window of time in the Paleocene-Eocene thermal maximum. We don't really have that in the Eocene-Oligocene of Nebraska. So we had to get a little more creative to understand where we are in the stratigraphy and how that relates to global climate and changes in mammals across that period of time. So just a quick map overview. So this little green in the very northwestern tip of Nebraska is Oglala National Grassland. So we have permits through the University of Florida to collect fossils from there and have been since 2014, though a lot of what I'm gonna talk about today has been collected in 2018, 2019, and then this past October when we were collecting things with a little more rigor. We look at the aerial view. You can see these vast expanses of these white rocks cropping out in Big Badlands at Badlands National Park, but there are wisps of these rocks really throughout southern South Dakota, across northwestern Nebraska, and then into Wyoming. If you haven't been to Badlands National Park, this is where the White River Group is most impressive. Unfortunately, when we look at the rock record, we seem to be missing about 1 million years of time right at the Eocene-Oligocene boundary. So we think there's an unconformity. We think there's a hiatus in deposition right at that 34 million year mark, going to about 33 million year mark. So it's really hard to see what's going on relative to climate in the animals that are preserved in the White River Group of South Dakota. In Nebraska, we don't have that issue. We think we have a pretty continuous record across this major climate event. So here's an example of an outcrop. So this is at Toadstool Geologic Park. So I'm sure many of you that have been out to this area of Nebraska collecting fossils have seen some of these outcrops at Toadstool Geologic Park. If any of you have not been out there and have plans to go to that part of the country, I highly recommend taking a half a day to kind of walk through Toadstool. It's really beautiful. I think the scale is sort of hard to grasp here, but we're looking at about 60 to 80 meters of rock here. As you walk a little bit further into the park, there are these sandstone layers, and within those sandstone layers, we get footprints of things like early rhinos and horses and birds that are really interesting. And there are fossils laying all over the park. It is part of the national grassland, so it is illegal to collect here unless you have a permit, but there are lots of ranches right in this area that are kind of paid to collect types of places. So if we look at this rock exposure, one of the most interesting parts is this little white wisp that cuts about halfway up the outcrop. And the reason this is so interesting to me as a geologist is this is actually an ash layer. So throughout the deposition of the White River Group, we get these little layers of about 7 to 8 ashes that we think are from aerosolized ashes and windblown ash that comes from New Mexico, Utah, Nevada. And what's great about these is these preserve minerals like zircons, where we can get radiometric dates and precisely date these layers of rock. So just a few years ago, there was a paper published that got new radiometric dates for this ash layer that puts that layer at 33.939 million years ago. This is pretty much coincident with the Eocene-Oligocene transition. There's a little bit of an issue correlating the marine rock record to the terrestrial rock record. So we're not 100% sure where the Eocene-Oligocene boundary falls in there, mostly because it has to do with the extinction of these small single-celled forams in the marine. So trying to figure out exactly where that is a little tricky, but more or less for the purposes of this talk, this demarcates the boundary between the Eocene-Oligocene. It also more or less demarcates the boundary between the two major rock formations that we see in the White River Group in Nebraska. So we have the Chadron Formation below this ash layer. So the Chadron are these river flood bank deposits, crevice splay deposits that are the deposition of which is mainly driven by these fluvial systems, by these river systems. Above that, we have the Brule Formation. In the Brule Formation, we see much less aquatic input in the geology. So instead, these are mostly windblown sands with a little bit of layers indicating there were some of these ephemeral streams kind of cutting through the geology. So we see just from the rocks alone that there is something going on at this period of time. We're going from a more wet environment to a much drier environment, likely tied into this global event. If we look at the biostratigraphy, we also have two North American land mammal ages that are more or less demarcated by this ash layer conveniently. So these are the Chadronian and the Arellan North American land mammal ages. These are defined by certain mammals that either go extinct at this boundary, but primarily by mammals that show up right at this boundary, such as the little micro deer, Leptomyrix, Evansii, that I'll talk about a little bit later. And as I said earlier, this more or less lines up with the Eocene and the Oligocene boundary. So if we plot the global climate curve next to this contact, we can see again that this is right in that period of time, about 33.94 million years ago, when we're seeing this major change in climate, this major drop in global temperatures, and the formation of Southern Hemisphere glaciation. Take a quick drink. So most of my talk today is going to focus on mammals because that's my area of expertise, but that's not all we find in Nebraska. And in fact, the herpetofauna, the amphibians and the reptiles do seem to be affected in a pretty big way by this climate event. We have things like pond turtles and other aquatic turtles that go extinct right at the boundary or are very rare after the boundary. as well as many other aquatic salamanders and lizards. But we also find things like birds. So this was an associated bird skeleton we found just below that ash layer. And this was actually found by one of the volunteers who came out with me in 2019, who works in our prep lab in Florida. And this is one of the most beautiful examples of a fossilized bird egg that I've seen in the White River group. One of the things we want to do is take a CT scan of this just to see if there's anything preserved, any embryonic bones, but also to look at the microstructure of the egg to see if we can better identify it. Again, primarily what I'm going to be talking about today is the mammals. So there are many archaic basal groups of mammals that we find in the White River group. These are things like these insectivores, apternodontids and leptictids. We get some early squirrel-like rodents, such as these ischiromyids, early carnivoran-like mammals, these hyenodontids, false saber-toothed cats, nimrabids, these big rhino-like perissodactyls that do go extinct. One of the groups that do go extinct right at that boundary, the brontotheriids, and then a lot of different groups of these artiodactyls, these even-toed ungulates. So things like these microdeer, hypertragulids, and leptomoricids. You get these really basal artiodactyls, even-toed ungulates, called the leptochirids. Maybe one of the more recognizable animals from the White River group, these antelodonts, these big hell pigs or terminator pigs that are relatively common in these exposures, but not quite as common as these guys, the mericoidodontids, which are oreodonts that are really, if you've been out there, you know how common they are. So we have many, many skulls of these guys. The taxonomy of them is a mess because we have so many preserved skulls of oreodonts. But they're very robust. I think the best way I can describe them is somewhat a cross between a pig and a deer, but they're all over the place during the Eocene Oligocene of North America. In addition to that, we also see lots of mammals that are recognizable today that are still around. So we have some early canids, some early dogs, early chrysetids, the group that today includes New World mice and rats, leporids, early bunnies, rhinoceratids, early rhinos, early horses, camels, and peccaries, as well as a few other groups like tapirs and stuff like that. So it's this interesting time of these really archaic basal mammals, but also this impressive group of mammals that we readily recognize as closely related to animals still extant today. So kind of getting into the field work now. So in 2018 and 2019, I took field crews in 2018 of several fellow graduate students, in 2019 of 3 undergrad students, out with me for 5 weeks in Nebraska. So we camped in the Badlands, crossed our fingers that we would have good weather and not so much rain in July and August, which can be tricky out there. And sure enough, the first field season in 2018, much of the first week was learning which roads we could drive on in our big van and which we couldn't. We had to call AAA a couple times to tow us out. So it's always fun when you're sitting in the Badlands waiting for AAA to come out over 24 hours before they can tow you out. But like I said earlier, this area of Nebraska is really beautiful. And on a clear day, you can actually see 40 miles north into the Black Hills of South Dakota. So it's a really fun place to do field work. And of course, there are lots and lots of fossils. So here are some examples of fossils we found over these 2 field seasons. We have a big brontotheriid jaw, and this thing is about 2.5 to 3 feet long. It's hard to get perspective on the scale here. We have lots of horse jaws that we found out there. This is actually an associated skeleton of one of those false saber-toothed cats, the nimrabids. This is an oreodont skull and lower jaws, another oreodont skull. And this is actually one of my first specimens that I found within the first 3 minutes of field work in the 2018 field season, which was a partial subhyrachodont rhino jaw. So finding fossils is not particularly tricky in the White River group of Nebraska, which is a fun place to be. I mean, I've certainly been in field work where we spent days and days and found maybe a fossil or two. That's not a problem out here in Nebraska. So we also went back out in this past October which was a totally different experience. So July and August, we typically have to worry about hot weather, dehydration, rain. These roads turn into what is locally known as gumbo. And unless you have four-wheel drive, it's really difficult to drive on these roads when they're wet. This past October was cold. We lost a day due to rain, woke up the next morning and had about half an inch of snow on the ground, 60-mile-per-hour winds. The wind chill was about 12 degrees when we left the cabin. Luckily, it warmed up through the span of the day. But it was only for 5 days. We really had to kind of push through and collect as much fossils and data as we could. In addition to collecting fossils, one of the other things that we're doing with this project that's relatively novel is we actually take survey equipment out to the Badlands. And what this GPS equipment is doing is it's marking every specimen we found to a sub-meter geolocation. So in latitude and longitude, we're talking about errors that are about a foot. And in elevation, we're talking about errors that are just slightly larger than that, but less than a meter in elevation. So this is a really exciting level of precision that we're able to get in terms of this GPS data. And as I'll show you, this really helps us to understand where all of these fossils are coming out of the stratigraphy, so that we're able to put those in a temporal context and understand what's going on through time relative to this climate event. So just a quick anecdote from our 2019 field season before I get back to the research part of things. So I showed this picture from earlier. So relatively early in the 2019 field season, we found this associated skeleton of a nimravid, the saber-toothed cat, that are relatively rare in the White River group. So you can see we have this vertebral column here. We have some of the hind limb here. We have some of the ankle down here and part of the skull preserved here. So we think that much of this is an associated animal. In 2019, I had 3 undergrad students with me who had never been in the field before. So I was teaching them proper jacketing techniques and teaching them about the data we collect with each specimen. So we were paying very close attention to the specimen as we were jacketing it, and eventually had to carry it out via tarp for about a mile because it was a 40 to 50 pound jacket. One day, so this took about maybe 2.5 days to properly collect the specimen. One day we happened to have service and one of our cell phones dinged and we got an alert about a storm that was heading our direction. And we promptly looked westward and happened to see this storm cloud. And very quickly thereafter realized that there was this funnel cloud that had sprouted from the storm. It was only about 10 miles to the west of us. So we promptly packed everything up, ran to our van and got out of there as quickly as possible, which for our affectionately named Van Gogh resulted in a lot of mud, a lot of dirt, a little bit of hail damage, but we made it out of there safe. So collecting in the White River group is an experience when you're camping. And in addition to this tornado event, which is the first tornado I've ever seen doing field work, we also had lots of hail damage, lots of wind damage. You're in the Great Plains, so we end up having to deal with this, several times a week in most cases, these really powerful storms that rush across the Great Plains and kind of screw up your plans for a successful day of field work. But they're good stories in the end. So after all of this, after 2,
Don,
yeah.
Don, this is Trish Kohler. Could you quickly go back to the picture of the hail for just
Absolutely.
a minute?
Yeah.
Thank you.
Sure.
All right, thanks a bunch.
Yeah, this, as you can see, this collapsed our main community tent quickly and resulted in inches of precipitation of the hail sort of around our camp. So it was an interesting day cleaning up from that for sure. I think this was a week after that tornado. So it was sort of one thing after another. This tent collapsed a couple of days after that, just from wind. This is my trusty tent that I had for years and years doing field work in the Great Plains. So it's always interesting. But after those 5-week-long field seasons in 2018 and 2019, and then this most recent week of field work this past October, we ended up with over 1,000 localities where we had GPS coordinates that precisely put us both in space, but also in terms of elevation too within the stratigraphy. And from those 1,000 localities, we have something like 4,500 fossil specimens. These are the specimens that have already been prepared and identified and cataloged. There's probably another 500 or so that require much more preparation. Lots of them Oreodont skulls, where they're waiting for and do the prep work. These aren't as important to my research right now, but we easily have over 5,000 specimens that we can pinpoint where they came from in the Badlands. So one of the other things we did is we didn't only pinpoint in terms of GPS data where these fossils were coming out of the Badlands. We also needed to know where they were in context to the stratigraphy we were looking at. So here is one of our main areas in the field. There are actually 4 main localities here. So this we call 33D East, 33D West, 33D South, and then 33B. And what's really exciting about this whole string of outcrops is it shows us that entire 1 million to 2 million year period from the beginning of the climate event all the way through. So up here in this area, we have that ash layer, the upper purplish white layer, the UPW. And then we have several other marker beds that are laterally consistent. We can point to and say this occurs at this point in the stratigraphy. And what we did is we also took GPS measurements of all of those marker beds. So now we have really precise GPS coordinates for all of those 5,000 fossils, and then close to 1,000 of these marker beds within the sections that we were really interested in. So once we have all these marker bed points, we use fancy geostatistical techniques to interpolate and extrapolate the bedding planes for each of these marker beds sort of across the landscape. So using ArcGIS, we're able to say that this bed sort of in this range, so you can see that this is where most of our points come from. So within this range of the bed, we have really precise elevation data for these marker beds. Once we get further away from that, it's a little bit difficult. So what we do is we extrapolate a plane, 3-dimensional plane across the landscape to incorporate a lot of other specimens that we found sort of in this area that were outside of the very local area of those marker beds, because they do dip into the outcrop, so it's hard to see where they are sometimes. And really the only way to figure out where you are relative to those marker beds is to drill cores. So hopefully sometime in the future we're able to do that. But for now, we're using these geostatistical techniques to figure out where these specimens are coming out from the landscape. So once we have these marker beds across these outcrops, we can then put all of the specimens that we found in these areas and do geostatistical calculation to say that this specimen is 10 meters above this marker bed or 5 meters below this marker bed. So for somewhere around 3,200 of those 4,500 specimens that are already identified, we have these really precise meter level estimates for where specimens are coming out of these outcrops. So a little side narrative here. One of the influences that I've had in this research is looking at the work that's been done in the Bighorn Basin and the Paleocene-Eocene thermal maximum. So I talked about this event earlier. It's a really good analog for modern climate change over the span of somewhere between 50,000 and 200,000 years. We see 6 to 7 degree C increase in global temperatures. And in the Bighorn Basin of Wyoming, we have a really great fossil record to see what's happening to mammals across that period of time. So here's one example that was published about 10 years ago, where the authors looked at changes in body size and compared that to what is happening with global temperatures. So in this case, temperature gets hotter towards the right. So we see this increase in temperature over a couple 100,000 years. And this is an estimate for body size from some of the, or really the earliest genus of horse, Cypropus. And what we see is early on in this climate event, we see a 30% decrease in size relative to this increase in global temperatures. And then we see an 80% increase once temperatures go back to background levels before the event. So what we think is driving this is something called Bergmann's rule. And the idea of this ecological principle is that as you get further from the equator, or as you get cooler in temperature, whether that's related to altitude, whether that's related to latitude, whether that's related to global temperatures, you tend to see smaller mammals when temperatures increase and larger mammals when temperatures decrease. And you can kind of think about this intuitively, right? You think about bears, for example. The biggest bears we know of today are polar bears. They live at the pole. This has to do with maintaining body temperature in really cold environments. But as you get closer to the equator, you have much smaller ursas that need to dissipate heat much more rapidly because the environment around them is much warmer. So there are times in the fossil record where we see this, and this is sort of driving some of the questions that I'm asking in the Eocene-Oligocene transition. So first, how can we systematically document responses in mammals to this Eocene-Oligocene transition? So as I've mentioned, this White River group has a lot of history and collection. I mean, there are numbers of us on the call that have collected fossils from this area, but this goes back to the earliest days of American paleontology in the West. Some of the first field crews hit the Badlands in South Dakota and northern Nebraska and collected it hard in the mid 1800s. Unfortunately, a lot of the collection since then just has not caught up with modern day technology. So in the 1940s, 1950s, there were major collection events that occurred in Nebraska and in South Dakota to try and document what was happening over this event. But the stratigraphic resolution is just not up to par with what we can do today. So what I'm trying to do is really look at these fine scale changes in mammals across this event, because the narrative really has been North American mammals are not responding to this event. However, in the marine realm, we really see these major extinction events in Eurasian mammals and African mammals. We see taxonomic turnover. We see responses relative to this global climate event. Why do we not see that in North America? In addition to this cooling, we also see drying conditions, which kind of brings in a complicating factor. Because cooling, if we're looking directly at Bergmann's rule for hypothesis, we should see mammals getting bigger in response to these cooling events. However, with drying conditions, we go from these more lush forests to more open grassland, kind of patchy forest habitat, where maybe the dietary quality of the vegetation just isn't quite as good. So we do see some complicating factors there, and I'll kind of dig into that. So just as a sort of as a kind of background of our collection efforts over those 3 field seasons. So this is what we call a violin plot. So these are 5 of the major localities where we are able to put it into stratigraphic context. So I've talked about 4 of these. We have pasture 33B, 33D East, 33D West, and 33D South. So these extend pretty much the entire range of that Arellan land mammal age, that earliest Oligocene age. But there's also another section we have that sort of leads up to that ash layer, that UPW. So this is just showing the frequency of specimens we've collected from each of these meter levels after we've gone through all of that GIS work and the geostatistical work. On the rightmost side of this graph on the right are our marker beds that we use. So here's the UPW. So this is that ash layer that we know is precisely dated to 33.94 million years ago. We have a sandstone unit that's about 13 meters above that. And then 3 meters above that, there's this laterally continuous green siltstone, and then an upper nodular green siltstone. And then we also took GPS coordinates of the boundary, the contact between the Arella member of the Brule Formation and the Whitney member of the Brule Formation. So we have all these 5 marker beds that are able to orient us in geologic time. So as I mentioned earlier, we're not 100% sure where the boundary between the Eocene and Oligocene is. We think it's right about here. The Chedronian, the Arellan, and Whitneyan are these 3 biostratigraphic North American land mammal ages. So the main contact that we're interested in is this contact between the Chedronian and the Arellan that occurs a few meters above this ash layer. And then lastly, we have lithostratigraphic boundaries. So we have the contact between the Chadron and the Arella just above that UPW, and then a contact between the Arella member and the Whitney members of the Brule Formation higher up at about 40 meters in this section. So we have a pretty good spread of specimens from just below the UPW all the way up to about 30 meters. So in this range, within this one locality that preserves this period of time, tends to be pretty steep. So it's difficult to find specimens there where the rest of this is relatively flat. So the main part of the study that I'm going to talk about today in terms of what we're seeing is looking at how body size is changing across some of the large mammals in the White River group during the EOT. So when we estimate body mass in the fossil record, particularly in the mammal fossil record, there are lots of ways to do it. Obviously, the more of the mammal you have, the more precise your estimate can be. So if we have a whole skeleton, we can get a really accurate estimate of body size. If you have a whole jaw, you can estimate body size based on the total length of the tooth row. Unfortunately, many of our specimens are just isolated teeth. So the best way that's been established to do this in the mammal literature is to actually look at the lower first molar and measure the length and the width. And this essentially gives us an idea of what the rectangle of the tooth would be like and what that area of the tooth is. And then to normalize all those data, we take the natural log of that length and width measurement, essentially occlusal area or the area of the wear surface of the tooth. And we've seen a pretty good relationship between size of the lower first molar or area of the lower first molar and body size in mammals. So because so many of my teeth are isolated teeth, although we do have handfuls of total tooth rows, total lower jaws or upper jaws. In the case of this, I'm more interested in comparing sizes within specific groups, within specific genera of the mammals from the White River group. So this is the way that I'm estimating body size here. So just a few graphs. So one of the more common mammals we have in the White River group is Leptomeryx. If you've collected in Nebraska, you know Leptomeryx is everywhere. So here's a lower jaw of Leptomeryx and the view, the occlusal view down at the chewing surface. We like to call these micro deer. So they look like really small deer, though they're not actually cervids. They're in their own family. And here's a graph for how body size is changing up this section. So don't worry about the colors here. This relates to what locality of those 5 localities the samples came from. On the x-axis here, what we're looking at is that area of both the lower first molar and the lower second molar to make sure we're seeing the same pattern in both. And then on the y-axis, we're seeing time in terms of meter level in this stratigraphy. So what we can see is there's not much going on here, right? So generally speaking, as we go up, here's the ash layer, we're seeing more or less the same body size. There's a little bit of an increase here, maybe a little bit of a decrease here, not a whole lot going on though. When we go to another micro deer, Hypertragulus, we see a different pattern. So we see quite a large variation of body sizes when Hypertragulus first shows up. So This is a deer that wasn't around before about 5 meters above the UPW. This is actually one of the defining species of that biostratigraphic contact between the Chardronian below and Arellan above, excuse me. So this is defining the start of the Arellan. So what we see is quite a large variation, and we see a decrease in body size as we go up, both in lower first and lower second molars. Then if we go to this little squirrel-like rodent, Ischyromes, we see a different pattern. So we don't have a lot of Ischyromes fossils from below the UPW. So these might just be two outliers, but it is kind of interesting that they seem to be much larger than what we see, just 10 meters above that. But once we get above the UPW, we see lots of small Ischyromes, and then above 10 meters, lots of large Ischyromes. So there is a very noticeable pattern here in terms of increase in body size. And if you look at the estimated body mass of this squirrel-like rodent, we actually see almost a doubling in body size over a very short period of time. And I'll dig into that in 1 second. One of the other really common animals we have from the White River group is the rabbit Paleolagus. And Paleolagus shows a very interesting but opposite trend to what Ischyromes shows. So both the lower first molars and lower second molars show a pretty definite decline in body size across the event. So if we look at all of this in sum, so here's a best fit line for all those four we just looked at: Leptomeryx, Hypertragulus, Ischyromes, and Paleolagus. We see about a 20% increase in body size in Leptomeryx, up to about 10 meters in our stratigraphy. Then we see a decrease by about 10% in body size after that. In Hypertragulus, we see a pretty consistent decrease by about 20% in body size. Ischyromes gets interesting. We see an increase by about double in body size very rapidly at about the 10-meter mark. And as we look at this, it starts to seem like this 10-meter mark is important. That's sort of where we're seeing these major shifts in body size happening. And then lastly, the small rabbit Paleolagus, we see a decrease by about 55% in body size in Paleolagus. So if we line that up to the climate data that has been collected from the White River group, we see with cooler temperatures on the right, warmer temperatures on the left, that Ischyromes, this small squirrel-like rodent, body size changes line up pretty closely with this climate curve, right? So you can almost see the sharp increase here in temperature, the sharp increase in body size, a few wiggles, and a few wiggles here. And it does seem, and this has been shown in the literature for more recent rodents, that it's tracking climate pretty closely. That can't be said for these other mammals. We're not seeing a whole lot of change in Leptomeryx. We're seeing a small decrease in body size in Hypertragulus. We're seeing a very significant decrease in body size in this rabbit Paleolagus. We're doing some other more detailed analyses in Paleolagus, and what's interesting is it does seem like the dentition, the teeth of Paleolagus, seem to be changing quite a lot over a very short period of time. So it almost seems like Paleolagus is being influenced pretty heavily by potential decrease in vegetation quality. So this might, we think, be driven by Bergman's rule, by this idea that as the climate gets cooler, things get larger. Paleolagus may be driven by decrease in vegetative quality. So just a few quick conclusions. So unlike the narrative that we've had for really 50, 60 years that mammals aren't really responding to the EOT in North America, I think these body size data show that they are. We do see changes in body size across this climate event, which is something that is relatively unknown to this point. So this is exciting. This is showing that these mammals are being affected by climate in some way. However, contrary to Bergman's rule, which would lead us to hypothesize that all of these mammals would be getting larger, we do see some mammals shrink. And quite possibly this is related to decline in dietary quality. As we go from these really lush forests to a more open grassland with a few patchy forests, that may be limiting the size of these mammals so that they do get smaller over the course of thousands of generations. Interestingly, body size in Ischyromes does increase by about double very rapidly in this section. And it seems to very closely track this climate curve that we have for the White River group, which is really exciting. We also have a lot of other projects going on with this work. So we're looking at changes in morphology, for example, looking at ankle bones in those micro deer and seeing if they become more adapted towards running, towards cursoriality due to the opening of the habitats. In the rabbits, as I was talking about, we seem to see suggestions of hypsodony very early in the section, where teeth are getting larger and taller to deal with these increased wear rates, and then adaptations to hypselodonty, where their teeth are ever growing, their molars are ever growing. And we're doing some isotopic work to see how diets are shifting before that climate event and then during and after the climate event. So there are many, many people that I need to thank for helping me with all this work. I received many grants to go out to Nebraska for months at a time to collect fossils. I've had dozens and dozens of people come out with me and help collect fossils in this very rigorous way in which we're collecting GPS data. And then lots of help once I brought the fossils back to get them identified, to get them prepared. So there are so many people that I need to thank for helping me with this. And I want to thank you for having me today. It's great to meet you all. Hopefully sometime soon we can meet in person. I'd love to get out in the field and really get the opportunity to jump into North Carolina paleontology and start to build the museum collections where we do have these gaps. So thank you, and I'm happy to take any questions.
I have a question.
Yeah.
Or just as I was listening to all this, I was thinking about things I've read or seen, like the whole idea that there were pygmy mammoths because their diet was restricted on islands.
Yep.
So it would seem to me maybe that would be a way to sort of see a similar correlation to the size of some of the specimens maybe that you've looked at too.
Yeah, and I think some of what we're seeing in terms of the shape of the teeth in things like these rabbits in Paleolagus, it seems to suggest that one of the driving factors of these microevolutionary patterns is dietary quality. And when we look at things like stable isotopes, we do see some shifts, though not as large as we might expect before this climate event and then during and after the climate event. So I think it's reasonable to hypothesize that some of the patterns we're seeing relate to some of this degradation of dietary quality. Any other questions? So I got a sense when I was kind of clicking through everybody. How many of you have been out to Nebraska before in the White River group? Emily? So about 6 or 7 of you?
I've been out there. This is Trish.
Great. So it seems like, yeah, 6 or 7 or 8 of you. So hopefully this gives you a little better context of what's happening on the larger ecological scale and global scale during the time that these fossils were deposited. I think it's
John,
a really fun place to.
John, this is Trish. Thank you so much for showing those great pictures of the jaws and the teeth. That will help me further identify the fossils that I found out there. Thanks a bunch.
Absolutely. And feel free to send me an email. I'll put it in the chat. I'm always happy to take a look at specimens and provide IDs where I'm able. So let me go ahead and put my email in the chat. And feel free to email me with pictures or any other questions that you might have about these specimens. So I do see a couple notes in the chat. So I see from Judy, shout out to South Jersey and Big Brook. Did you grow up in South Jersey? Judy, are you from South Jersey?